Hello everyone, welcome to my videos on elementary differential equations. This is video number 22 for chapter 3. In this video, we'll give further examples on the spring mass model. In fact, we will look at damped free vibrations, which will be explained soon. So let's recall the spring mass model, which is given by this differential equation, mu double prime plus gamma u prime plus ku equals F. M is the mass, gamma is the damping constant, k is the spring constant, and F is external force. So we now consider damped free vibration, meaning that gamma, the damping constant, now is not zero, okay, and it's never a negative constant, so it's actually now strictly bigger than zero. And the free vibration means there's no external force, so F is zero. So basically we'll just have this homogeneous equation with zero on the right hand side. So this is a constant coefficient second order homogeneous equation. We know how to solve it. We will write out the characteristic equation, which is m r squared plus gamma r plus k is 0. And this is a second order polynomial. In the general setting, we can write out the two roots r1 and 2 to be following: negative gamma plus minus square root of gamma squared minus 4km over 2m. And we see that we have a square root of this quantity, which is called the discriminant. And then the type of the roots will very much depend on the sign of the discriminant or its quantity. It might be real valued, it might be a complex number here if this term shall be negative. So for simplicity of notation, below we will denote this quantity to be capital delta. Okay, so let me repeat here. The roots are negative gamma plus minus square root of delta over 2m. Delta is gamma squared minus 4km. The first case, when delta is strictly bigger than 0. So what does it mean? That means this quantity is strictly bigger than that quantity, which means gamma is strictly bigger than square root of 4km. And gamma is the damping constant. If it is big, that means you have more damping. So this describes the case with a large damping. So in this case, we see that we will have two roots, because what's under square root now is a positive, strictly positive quantity. Okay, so if we write the two roots in order of their size, r1 will be negative gamma minus the square root of the delta, and then the second one, r2, will be negative gamma plus the square root of this delta. So this we take the negative square root, and here we take the positive square root, and then both divided by 2m. So one comment I want to make is the sign of the two roots. So r1 is this. So remember, gamma is always positive, and we're taking the negative root, so we have two negative numbers on the top, so this r1 is clearly negative. It's a negative real number. And for r2, we have this number, negative gamma is a negative number, but it's plus the root, so the positive square root of that term. So this one is a positive number. So can we know for sure the sign of r2, meaning what is negative gamma plus the square root of that? Well, recall our assumption. Gamma is strictly bigger than 4km. So if you don't have this term 4km, then you take the root of this, you will just get gamma, and you get negative gamma plus gamma is 0. But now you subtract a non-zero amount for Km from the gamma square. Therefore, the quantity here will be strictly less than gamma. And then negative gamma plus something less than gamma will be less than 0. Okay? So R2 is also strictly negative. So both roots are real and negative. Okay, then we can set up the general solution, which will be exponential function with the two roots. They're both negative, e to the r1t, e to the r2t, and we do a linear combination. And then we see that, how was this vibration doing? Well, we see that since both r1 and r2 are negative, as time goes, the vibration will approach 0 exponentially. Okay, so this is caused by the large damping force. Then there will be no actual vibrations in the motion because everything's damped and it's so sticky, and the mass will just simply return to the equilibrium. That's where you equal to 0 at an exponential rate. So this kind of a motion where you have lots of damping is called overdamped. Now let's look at the second case. This is the case where delta equals 0. So that is equivalent to say this equal to that. So gamma is square root of 4km. It equals. So in this case, we have less damping than case 1, where gamma is strictly bigger than this quantity. So in this case, and the square root of 0 is 0, then we have double roots. R1 equal R2, let's just call it R. That will be negative gamma over 2m, because that term is 0. Okay, and we can also see right away that m is positive, so this double root is less than 0. Okay, so in this case, we can write out the general solution, which is one is exponential function, the other is exponential function times t. So we can write in this form, c1 plus c2t times e to the rt. Okay, so the oscillation, if it really oscillates or not, will depend on the sign of c1 and c2. So, and these signs are determined by the initial condition. Then it is not hard to show that this will cross the equilibrium at most once. So you could start U positive, and then it could cross 0 once and become negative, and then it will just exponentially approach 0 because the exponential term here will dominate the motion after a while. Okay, so this kind of a motion has a name. It's called critically damped. And the value here, the damping constant gamma, this value here is called a critical damping constant. Now, the final case, case 3, is when the discriminant delta is less than 0. That means gamma square is less than that, then gamma is less than square root of 4km. So here the damping is small. It's smaller than the critical damping. So it's a case for small damping. So small damping basically says it's easier to move. The medium would offer less resistance for you to move around. Okay, so in this case, we know that this quantity is negative. Then we have complex roots. And the real part is negative. Okay, let's write out R12 is negative lambda plus minus mu I, where lambda is the real part. Negative lambda is the real part, and then lambda is gamma over 2m. And the mu is the imaginary part, which is the square root of that, which we write into 4km minus gamma square. So that guy will be positive, okay, over 2m. And then we can write out the solution. The general solution is an exponential function times cosine and sine. So the exponential function has the real part as the exponent and multiplied by sine and cosine, where the imaginary part goes as in the frequency of the oscillation. So as we have seen from the solution with the complex roots with the negative real parts, and we see that this is the periodic motion. It gives you oscillation, and the function in front of the oscillation gives you the amplitude. So you have something that oscillates, and with the amplitude exponentially becomes 0. So it will oscillate big and become smaller and smaller and smaller and eventually settle down to 0. Okay, so this type of motion is called damped oscillation. Okay, so we can also be more specific and rewrite this in terms of the amplitude and the phase. So we know a term like this we have manipulated can be written as r times cosine mu t minus the phase, where this r is just c1 squared plus c2 squared square root. This is a manipulation we did in the previous video. Okay, and then delta is the phase. It's arctan of c2 over c1. Okay, and then if you write it like this, and then you see more clearly the solution takes this form, where this will be the amplitude of the oscillation, and then ut is called quasi-frequency, because it's not actually a periodic motion, but it oscillates, so it's not a frequency, it's a quasi-frequency. And then 2 pi over mu is called the quasi-period. Okay, let's summarize. So we have 3 cases, but we see that for all the cases there is a common feature, that is, the real part of the roots, no matter in which case you are in, they're always negative. And that causes the solution ut here to eventually go to 0 as t grows to infinity. So this means that if there is damping, here we have, remember at the beginning we assumed gamma to be non-zero, so it's just strictly bigger than 0. If damping shall exist, no matter how big or small, it doesn't matter that in the end the motion will eventually come to a rest. Okay, now let's take an example. So it's a word problem. It says, let's read through it. A mass of 1 kilo is hanging on a spring with the spring constant K equals 1. And the mass is in a medium that exerts a viscous resistance of 6 newtons when the mass has a velocity of 48 meters per second. And the mass is then further stretched for another 2 meters and then released from rest. Find the position function u of t of the mass. Okay, so let's look into the details. So to set up the problem, we know that we need m, k, and gamma. So m is the mass, m is 1. This is given a mass of 1 kilo. And then the spring constant k is given, k equals 1. But gamma is not given. But there is the sentence. It says, a medium that exerts viscous resistance, that is 6 Newton, when the velocity is 48. Okay? And the ratio between them is exactly this resistance. So the damping gamma is 6 over 48 and can be simplified as 1 over 8. Okay, now we can put these numbers in and write out the equation for u. So m u double prime, m is 1, plus gamma u prime, gamma is 1/8, plus k u, k k is 1 equals 0. There's no external force. Now we need to identify the initial condition. So u of 0, what is the initial position? Well, it says the mass is further stretched for another 2 meters. So it's 2 meters away from the equilibrium in the positive direction. So u0 is 2. And then it says it's released from rest without initial velocity. So u prime 0 is 0. Okay, now we have our equation and we have our initial conditions, and we can go ahead and solve it. So the standard procedure, set up the characteristic equation, put r squared here, r here, and 1 here. That's what we have. And then we solve this polynomial of degree 2, and we find the 2 roots. They are complex. R12 is -1/16 plus minus, and this guy here, square root 255 over 16 I is the imaginary number. And then we know the term in front of the imaginary number will be the term in front of t in sine and cosine, and let's call this guy omega naught, and that is the system frequency. Okay, then we can write out the general solution, which is an exponential function of the real part of the solution, -1/16t, times a linear combination of the sine and cosine function with the omega naught t in the function. So it's c1 cosine omega naught t plus c2 sine omega naught t. And here the c1 and c2 are 2 constants to be determined by applying the 2 initial conditions. Okay, let's try that. So the first initial condition is u0 equals 2. Set t to be 0, e to the 0 is 1, cosine 0 is 1, sine 0 is 0, so I just get c1. So this gives me immediately c1 is 2. The second initial condition involves the derivative. Okay, so let's first write out the derivative. So it's a product, this function times the sine and cosine. So if we differentiate the exponential function first, we got a factor 1/16 in the front, and the rest remains the same, so it's ut here. And then plus, we keep the exponential function, and then we differentiate the sine and cosine. So differentiate of cosine gives me negative of sine, and I carry omega naught as a constant out. And then differentiating sine, you get cosine, and then you have omega naught in the front. And now we can plug in the initial condition. u0 prime will be equal to, put t to be 0, so 1/16 u0 plus, and then when t is 0, this is 1, and this sine of 0 is 1, sine of 0 is 0, cosine of 0 is 1, so I just get omega naught c2. Okay, and then we know that u naught is just 2. So c2 is the only unknown here, and we can quickly solve it. Omega naught we already know. And plug in the numbers and you simplify, you get c2, which is 2 over square root of 255. Okay, now we can put back these 2 constants in the general solution, putting c1 and c2 to be 2 and this number. We can write out our function. So u of t is this exponential function with negative exponent times a linear combination of sine cosine with this coefficient 2 and 2 over square root of 255 in front of the sine function. Okay, so then we solve the problems, and that's the end of this example, and it's also the end of this video. And this is all I have to say about free vibrations. So in the next video, we'll consider a vibration that has a source term, which is called the forced vibration. Okay, I hope you enjoyed this video, and I look forward to seeing you next time.